Okay, so here we go. It's part 2 of section 5.8. We're doing integration. Here's my problem. I have been handed this integration problem. I look at the integrand, I recognize a fraction. Okay, it's not plain old integration. Numerator is not the derivative of the denominator. I got a t to the fourth downstairs. The numerator would have to be t cubed for it to be the derivative, so it's leaving out that u prime over u logarithm business. I don't see substitution working for the same reason. If t to the fourth was my u, then 3t or 4t cubed would be derivative. No, I got a t. Oh, but wait a second. This is kind of like this one we just did. The t to the fourth and the t, and it worked out to be arc-trig, so maybe this is arc-trig too. So I'm going to go back and look at my arc-trig formulas. I don't think it's that arc-sine one. I'm thinking it might be this one, because there's no root in the denominator. It's the sum of two things. So I think it's the 1 over a arctan 1. So I'm going to copy that formula down. Let's see. The integral of du over a squared plus u squared is 1 over a arctangent of u over a plus c. I'm just going to make sure I got that formula right. I know it's right here. Yeah, I got that formula right. So if these are going to be, or this is going to be the formula, then I've got to make all of this match up, right? So let's see. T to the fourth plus 25 has to be the a squared plus u squared, which means that a has to be 5, and u has to be t squared again, which means differential du is 2t dt. Okay, so things are looking good. All right, I'm going to show you a trick here that we haven't used before. Rather than modifying this to match the integrand, I'm going to modify the integrand to match the du. I'm going to put a 2 here. Whoa! I'm going to put a 2 here and a 1/2 out in front. Actually, you know what? I'm going to do that in a different color so it stands out better. I'm going to put a 2 here and a 1/2 out in front. Now, the 2 and the 1/2, if you multiply them together, equals 1, so it really didn't change the value of the integral. But now, 2t dt matches my du part over here. And it would be much easier to make this substitution work. Okay? All right, so then doing this, it looks like everything matches up perfectly, and I can just go straight to the answer. There is the extra 1/2 from out in front, and I'm going to get the arctangent of my u, which is t squared over a, which was 5. Oops, I forgot the 1 over a. So a 1 over 5 also, plus c, and then the 1/2 times the 1/5 would be 1/10. Arctangent t squared over 5 plus c. Well, that wasn't too bad. And the reason it wasn't too bad is because I'd seen one like it before and I knew exactly what to do right here. So what I'm sure you've noticed by now is something's hard the first time you see it. It's a little bit easier the second time you see it, and it's going to be even easier every time after that. Because that's just kind of how math works. First time's hard, second time's easier, third time's even easier. Okay. All right, let's take a look at this one. I have the integral of, I see a fraction in my integrand. Okay. I've got a numerator. I've got a denominator. Derivative cosine is negative sine, but maybe u substitution is the way to go. Let's try it. If I say that u is cosine x, then du would be negative sine x dx, or negative du is positive sine x dx. And then if I did my substitutions, I would get negative 1 times the integral of du over 7 plus u squared. But That didn't fix it because this is not now an integral that is easy to do. So it looks like U substitution was not the way to go. Well, if U substitution isn't the way to go, then what is this thing? Well, a little bit harder to see, but do you see that the denominator is the sum of two terms? And that one of them is a something squared? So maybe this is arctangent again. I see a fraction. Downstairs is two terms added together. One of them is a function squared, and the numerator is the derivative of that function. Not the function squared, but just the derivative of the function. Okay? So if I'm making the argument that I'm looking at du over a squared plus u squared, which is going to be rewritten as 1 over a arctan u over a plus c, then 7 plus cosine squared better be a squared plus u squared. So then a is the square root of 7, u is cosine x, differential du is negative sine x dx, which means that negative 1 times du would be our positive sine x dx. And it looks like everything is going to work. Everything is going to end up giving me this lovely integral that I want. Right? Now, two things about this problem are hard. One, it's hard seeing this relationship. And two, many people don't like this. They think that since this is a squared, that this number right here needs to be a perfect square. It doesn't. It just needs to be something you can take the square root of. It has to be a positive number. So then putting it all together, what do we get for our final answer? Well, we've got an extra negative 1 times 1 over a, which is root 7, arctangent u over a, so u was cosine of x, divided by a, root 7, plus c. And if you want, you could clean this up right here and then just say that this is negative 1 over root 7 arctangent cosine x over root 7 plus some constant c. Good to go? All right. Harder still. I've got a fraction for my integrand. Denominator is squared, the numerator is linear, so maybe this is u substitution, where u would be x squared plus 1, and then du would be 2x dx, or 1/2 du would be x dx. But that doesn't work because of this stupid negative 3. Well, that doesn't help me. And I can't just fix a minus 3, a subtraction of 3, because it's not a coefficient. Okay. Well, I'm not sure what to do, because it doesn't look like trig, arc-trig, because this was arc-trig, then this would be the u squared plus a squared. This would be the arctangent one. But then this up here isn't just du, again, because of that stupid minus 3. You know, if that minus 3 wasn't there, if it was just x upstairs, life would be good. So let's do that. Let's rewrite this problem and say this is x over x squared plus 1 dx minus 3 over x squared plus 1 dx. And why did I do that? Well, I saw when I was attempting to do plain old substitution that this would have been good for plain old substitution. And I saw that this would have been good for plain old arc-trig, if that was just there. So I made it happen. It's kind of like what we did in the last section where we added one and subtracted one to that u term to make it do this. But we were just doing it because it was already sitting there in front of us. Right? So over here on the left, I'm going to use substitution. I will say that u is equal to x squared plus 1. That means that the differential du is 2x dx, or that 1/2 du is just x dx, which means that this first integral is going to become 1/2 du over u, which gives me 1/2 natural log absolute value of u, which then back substitution gives me 1/2 natural log absolute value x squared plus 1, but since x squared is always positive, or at worst 0, x squared plus 1 is always going to be positive, so I can ignore the absolute values. Now that's only the first one. I still have to do minus, so I'm only working on the left part of this. Over here I said this is going to be arc-trig, okay? Because we are going to make the argument that x squared plus 1 is the u squared plus a squared. So u is equal to x, differential du then is dx. We're saying that a is equal to 1. And so then this piece over here becomes 1 over a arc tangent u over a. And then, of course, we're going to put in the plus c over here because there's always a plus c, cleaning that up a little bit. And skipping a few steps, I'm going to go straight down to here and say that this is arctangent x plus a constant c. And then this is our final answer. Okay. So how did I know to do that? How did I know that this was going to work in this way? Well, because I tried the other things that I would like to try. I never want to do arc-trig. I hate doing arc-trig. It's the worst one. So that's the last resort when nothing else works. So I tried plain old substitution, and I saw that plain old substitution, the 3 was a problem. And then I looked at it for arc-trig, and I saw that the x was the problem. So I said, well, if this x wasn't here, it'd be arc-trig, and if this 3 wasn't here, it'd be substitution, so let's rip it apart, because I can do that. That is just the difference in this case of 2 fractions. And so I can write it as a difference of fractions and integrate each of them independently. One integrates with substitution, one integrates with arc-trig. Now, at some point, you are going to get good enough at this if you do this enough that you can go directly from that line right there to the answer, because you'll see it. Right? And I just realized I made a mistake in this problem. I lost my 3. So what does that mean? There should have been a 3 right there times that, which means there should be a 3 right here times that. It's a good thing I stared at that for a while. Now I feel better about that. Okay. All right, last problem. Last problem. Last problem. Last problem, last section, last problem. Here I have the integral of dx over x squared plus 6x plus 12. I've got a problem. I don't know what to do. I'm looking at it. I'm seeing a fraction. Okay. The numerator is not the derivative of the denominator. If that denominator was my u, then my differential du would be 2x plus 6 dx. And I definitely don't have that upstairs. And constants and coefficients can usually be fixed by adding or subtracting or multiplying or dividing by a number, but I can never fix a missing variable. And that would be missing a variable, so I'm in trouble. So I'm going to have to try something else. All right. I am going to try a technique where I am going to force this into arc-trig. I need my denominator to be, a squared plus u squared, or u squared plus a squared if you prefer. Addition is commutative, doesn't matter. I need it to be a constant plus a variable term squared. So I'm going to force that to happen. I'm going to do something on that denominator that you probably haven't seen in a while. Do you remember completing the square? And so I get x plus 3 squared plus 3. So I can rewrite my integral as 1 over u squared plus a squared du. Because if this is my u squared and this is my a squared, then u equals x plus 3. du is just dx. A squared is equal to 3. That means that a is just the square root of 3. I've got arctangent sitting right there talking to me. And so then this integrates into 1 over a times the arctangent of u over a plus c. Now, once you know the trick, that problem is very straightforward, right? So what was the trick? The trick is, I looked at it and I realized that I have a quadratic on my variable x downstairs, and I have nothing upstairs. Essentially, I just have 1 upstairs. I don't have the derivative of an x squared anywhere. So that means I'm looking at arc-trig if I can find a way to get u squared out of that. So over here, I did completing the square. And where did that 9 come from? Okay. Well, in completing the square, the constant term of the trinomial is half of the coefficient of the linear term squared. So I took the 6, divided it by 2, squared it, 3 squared is 9. But the green 9 that I added here, I had to subtract there, otherwise I'm adding 9, and if I don't subtract the same 9, I'm going to change the value of the expression. So plus 9 minus 9, everything is good. Everybody's happy because that expression, the entire expression, stays with the same value. It's x squared plus 6x plus 9 minus 9 plus 12. All right, so once you know the trick, relatively easy problem. In fact, I think that could be said as true for all of these. Once you know the trick, relatively easy problem. Once you know the trick, relatively easy problem. It's those tricks. It's seeing that and then applying it to a new situation that truly is where it's going to be useful. Okay? Rarely will you ever see one like this. That's just too straightforward. We have to make it more complicated. It's math. If it was easy, we'd call it basketball or something. We have to make it complicated, so it's calculus. It can't be calculus that was easy. It has to be calculus that was hard. All right, this brings us to the end of section 5.8, which also brings us to the end of the entire course. Calc 1 is in the books. You'll have this exam for chapter, exam number 8, with sections 5.4 through 5.8 on it, and the final exam coming up. Right, the final exam will be Monday through Thursday of final exam week. So finish this up, take the last exam, and then prepare. Best way to prepare for the final exam is to take a look at old exams. Okay, go back through all the exams, go through the grade book and review the exams, because that's where I'm going to draw the material from. Okay? All right, have a good day.